All right, hello everyone. Welcome to Math 380. This is your video lecture for the day. I am recording this in cloudy New York City, so I miss you all very dearly and hope to be back with you soon. But in the meantime, we have some convexity to discuss. So today I'm going to just kind of finish up the section on convexity, and then we'll talk a little bit about classification problems, and then start setting the stage for logistic regression. So very exciting stuff today. I'm looking forward to it. So recall we talked about convexity on Wednesday, and we say that a function f is convex if for every pair of distinct points p and q, and for every value of t, real number between 0 and 1, if this inequality holds here. Now, remember what this is saying is inside of this inequality, or inside of this function here, this is the line between p and q. This is the line segment that connects p and q. And this here is the line segment that connects f of p to f of q. So what this expression here is saying is that a function is convex. Let me move this over here. Maybe I can do that so you can see better. Okay. A function f is convex if, when you plot the graph, you have this nice property that for any, well, let me draw it like this. For any 2 points in the domain, say p and q, wrote them backwards, if you connect f of p and f of q with a straight line, essentially the graph of the function between p and q has to live below the line that connects f of p to f of q. So this is f of q, this is f of p. So the graph of the function between p and q has to live below the line, the straight line that connects f of p and f of q. So an example of a graph that's not convex would be something like this. Okay, because I can pick, oops, I did it in green. Not that it really matters, I just like to be consistent. Okay, so something like this is not convex because if you let this be p and this be q, you look at f of p here and f of q down here, the straight line connecting them doesn't live above the graph, okay? Or the graph doesn't live below that straight line. There's this portion right here where it passes above, okay? Now, strict convexity is a slightly stronger sense where we want that inequality to be sharp, okay? Instead of less than or equal to like we get in convexity, we want it to be strictly less than for every t that is strictly between 0 and 1. And so what this does is it precludes things like the following. So for example, if I draw a linear function like this, the graph of a linear function, this would be convex because for any choices of p and q here, this is f of p and this is f of q. And when I connect them with a straight line, notice that straight line matches right up with the function or the graph of the function. And so certainly the graph of the value of the function is less than or equal to. In this case, it just happens to be equal to the value on the straight line, okay? But essentially this type of situation is convex, but not strictly convex, okay? So strict convexity precludes us from having situations where our line is flat or our curve is linear like that, okay? So as mentioned before, the nice thing about convexity is that optimization problems end up working out much nicer than they typically do. Because we know that for a convex function, we know that we don't have any local minima that aren't global minima. So essentially what this theorem here is telling us is that if C is a local minimum, it implies that C has to be a global min. Okay? Now this has a few other implications. So for example, when f is differentiable, in other words, when f has well-behaved derivatives, or rather just you can compute the derivatives, then what that tells us, well, let me write it like this. So if f is differentiable and nabla f of c equals 0, what this implies then is that c is a global min. All right. So notice I should say, assuming, let's make this assumption. Let's write it like this. So assuming, well, don't leave it like that. So if f is convex, then, okay, so both of these statements I just made are assuming that f is convex, and so if f is convex and c is a local min, then c also has to be a global min. If f is convex, f is differentiable, and nabla f, or the gradient of f at c, is 0, then c has to be a global min. Okay. Now for strict convexity, well, this tells us so one thing to note is that if so you might see this statement here, and you might say, well, hey, the local min has to be a global min, therefore there is only one global or local min. There's only one point that sort of is a global min, but that's not the case. So note, convex functions can have multiple global minima. Okay, and it's not too hard to draw a function that does that. I'll give you a second to think about it. Can you think of a function that is convex and has multiple global minima? Well, I can. I'm going to draw it like this. Oops, that got too straight on me. There we go. So something like this, and then let's just draw like a straight line across here, and then back up. Okay, so in this case, notice that along this line here, all of these points are global minima. Okay, so there's actually infinitely many global minima in this case. Okay, but notice that if my function is strictly convex, then a flat portion like that can't happen. So we can say something stronger. So let's say, however, if f is strictly convex, then it has at most one global, and in fact local too, minimum. Okay, so if you're strictly convex, then you can't have one of these situations going on. You can't have a flat portion like that. Therefore, for strictly convex functions, there is exactly one global minima. Well, I shouldn't say there's exactly one, because can you think of a strictly convex function that doesn't have a global minima? Okay, what if we did something like this? Oh, change colors. Something like this, where you go off to negative infinity. Okay, so this would be strictly convex, right? However, if I kind of keep sailing off to negative infinity, well, let's actually give you a concrete. You deserve an actual concrete example here. Well, you deserve one. That doesn't mean I can give you one. I could write one out, but okay, I don't have one on the top of my head, but something like this would work. As long as you're sort of always going down, you can go off to negative infinity as you travel to the right, and you'd never have a global min. Okay, so it doesn't always have. So it doesn't always have a minimum, but when it does, it's unique. Okay, so a bunch of nice sort of facts about convex functions here. Every local min is a global min. If it's differentiable and the gradient vanishes, then that means that it has to be a global min. C has to be a global min. And for strictly convex functions, when they do have minima, those minima are unique. So let's see if we can prove this theorem. I'm going to just copy it and restate it down here. Okay. So what is this theorem telling us? It's essentially, if you're a local min, then you have to be a global min. So let's write down some assumptions here. Okay. So proof. Let's suppose that C is a local min of the convex function f. Okay. Now, we want to show that because it's a local min, it has to be a global min. Okay. So let's assume, we're going to do this to the contrary, assume by way of contradiction so assume to the contrary, or I should say, I didn't actually state what I'm doing the contrary. So assume, let's say assume by way of contradiction that C is not the global min, a global min. And that, so what would it mean for C not to be a global min? Well, it would mean that there exists a point P, or let's call it Q, with f of Q strictly less than f of C. Right? So if we're assuming that C is not a global minimum, then that means there has to be some point where the function is less than f of C. Okay? So we're assuming that that's the case, that there is some point where some point Q where the function is less than f of C. So let's invoke our concavity. So then by concavity, that's just sort of a $10 word for concaveness, which I don't think is an actual word. So by sort of concavity, we know that this thing here is less than or equal to 1 minus t f of C plus t f of Q. Okay? And since notice that f of Q is assumed to be less than f of C, we can replace f of Q with f of C, and we're only going to be making this thing bigger. So this gives us 1 minus t f of C plus t f of C. Now if we simplify all that, this is just equal to f of C. All right? So what this tells us is that maybe it's time for a picture break. Essentially what we've done here is, I mean, that the intuition hopefully behind this proof should be kind of not too hard to see. So if we're assuming that this is sort of C, and this is f of C, and that there happens to be some Q value where my function is less than f of C, then if we connect these 2 points with a straight line, notice that line is going to be downward sloping. Okay? And so essentially every point along the line, right? Every point along this green line, right? If you look at the function values of that point, that the function values along that line will be less than f of c. All that is really saying is just as you travel along this line, you're going downhill from c to q because f of q is less than f of c. So really all this is saying is that points along that line will all be less than f of c. Okay, and I guess I should say here, for t bigger than 0. Okay, yeah. So for t bigger than 0, all the points along the line will be less than the function value at c. So what that means is we're going to try to find a contradiction, and the contradiction will lie in the fact that if c is a local minimum, then that means that there should be some little neighborhood around c such that on this little neighborhood, the function never takes a lower value than it does at c. Meaning the graph of my function should never dip below f of c here. Okay? So to get to that contradiction, so here, so now let's let p of t be the point 1 minus t c plus t q. Okay, so this is just a point on the line. This is just a point on the line between c and q. So this kind of lives in our domain. Okay, and what I want you to notice, if we measure the distance between p of t and c, we want to see how far apart these are. Well, if I replace p of t with the thing that I've just defined it to be, which is 1 minus t c plus t q, and then I subtract off c, this thing here, when I simplify, I'm going to have a plus c and a minus c are going to cancel, and I'm just going to get minus t times c plus t times q. Okay, and if I pull the t out, I can do that. I can pull the t out and it picks up an absolute value there. Well, I guess t is greater than 0, or greater than or equal to 0, so I don't have to worry about the absolute value. I can pull the t right out, and I get the absolute value of q minus c. Okay? So what was the point of that? Well, the point of that is to show that no matter how small of a little window, I keep recording myself. I don't want to do that. I want my laser pointer. There we go. No matter how small of a little window I pick around here, say I pick a little window that's like size epsilon, okay? So like this distance here is epsilon, and so this is like c minus epsilon and c plus epsilon. Well, I can take epsilon to be as small as I want, but notice that no matter how small I pick epsilon, I can always, well, let's say it this way. So no matter how small I pick epsilon, I can always pick t so that it's small enough so that this thing here is less than epsilon. Okay? In other words, because what I've just shown is I've just shown that the distance between this point p sub t and the point c is just t times the distance between q and c. Okay? So this thing here is some fixed value. Okay? So maybe this is like, 2. But by showing this, because I have sort of full control over what t is, I can pick t to be as small as I want. And by picking it to be really small, I can make it always less than epsilon. Okay? And so what this does is essentially it's saying, when I look along the line from c to p, I can always pick t to be small enough so that I land in this little epsilon window. Okay? No matter how small epsilon is, I can pick t to be small enough so that the point that I'm looking at, the P sub t point, lives in here. Maybe it's worth drawing a separate picture here. It's a little bit bigger. Okay. All right, so here is my C. This is my f of C. Here is my Q. This is my f of Q. Okay, and my point P sub t lives somewhere in between C and Q. Okay, so it's somewhere in between C and Q. And all that previous proof was showing is that no matter how small of a little epsilon window you pick around C, you can always pick t to be small enough so that this point lives within that window. Okay, or in other words, so that the distance between P, T, and C is less than epsilon. Okay, well, why is that helpful? Well, I know, so I know from what I proved above that the value of the function at P of t, which is just the value of the function at 1 minus t c plus t q, this thing, remember up here, I proved that this thing here is less than f of c. Okay, so notice what I've done is I've shown that no matter how small of an epsilon window I pick, right, some little window here, I can always pick a point P of t that lives within that window, and the value of the function at P of t, which is this thing here, is always going to be less than f of c. Okay? Now, because I can do that for any value of epsilon I want, no matter how small, that means that there's no little window around C in which the function is sort of, in which C looks like a local min. For every little window around C, I can always find a point inside that window where the function is smaller than it is at C. And what that does is it contradicts the fact. So this contradicts the fact that C is a local min. Okay, and because we have a contradiction, what this tells us then is that no such point Q with f of Q less than f of C. Oh, that's just sloppy. Exists. Okay, there's no such point. There's no point in my domain that takes a lower value than the function does at C. Okay, so that proves that every local min also has to be a global min. Okay. Any questions? None? You understood all that? Okay, well, we'll roll ahead then. So the last thing that the next thing that I want to talk about, I'm excited for this section because we get back to some more probability stuff. I love probability stuff. I love maximum likelihood estimates and maximum any sort of estimate, maximum whatever estimate. If I get to use Bayes' rule, at least once in a day, I consider that a good day. Okay, so I might not be able to use Bayes' theorem right now, but we're going to set the stage for some nice use of Bayes' theorem in a bit. Okay. So what we're going to talk about now is what's called logistic regression. And we're going to do a lot of setup here and do a lot of sort of like nice analysis. But a logistic regression, you can think of it as basically just a very simple neural network. Okay. And so if you've seen neural networks before, logistic regression is kind of a very simple form of a neural network. But because it's simpler, we can sort of analyze what it's doing a lot easier. And so this will be kind of the way we step up into neural networks. All right. So the idea is, suppose we have a data set D, and I'm going to write these data points as x1, x2, up to xm. These live inside of some Rn. Okay. Where each xj belongs to one of k classes. So we've got classes C1, C2. Was it your class that didn't like the way I was doing my C's, my fancy script C's? Maybe it was my calculus class. One of my classes doesn't like the way I do C's, and I think that you're 300 level math students, so I think probably wasn't you. Probably was the calculus class. They thought my C's looked weird, so I'll do them capital C's like that. Okay, so we want to introduce a few probabilities here. So if I give you a data point X, and I want to sort of model the probability that that data point X lives in class. Well, actually, let me say one or two things here. So what could these data points be? Well, for example, these data points here could be images. So maybe they're just vectors with pixel data, and maybe each of the image, has some kind of barnyard animal, and so maybe X1 lives. Maybe the set C1 is the set of all images that have cows, and C2 is the set of all images that have horses, and CK is the set of all images that have chickens, and whatever other barnyard animals you like. There's a class for each barnyard animal, okay? And so the goal is if I give you a new vector X, say I give you a new vector XJ, and you've never seen it before, you don't know if it has a cow or a chicken in it, what we'd like to do is we'd like to come up with some way to sort of predict whether, this new data point lives inside C2, whether it lives inside CK, whether it lives inside C1, etc. So we'd like to come up with, this is what's called a classification problem, where we have a bunch of data sets and we have a bunch of data points, and we can think of each data point as living inside some class. You can also think of it as your data points having labels attached to them. That's sometimes also a convenient way to think of it. So given a data point, let's let P of Cj of X be the probability, the conditional probability that X lies in class Cj, okay? So this thing here is just gonna, I've given you a data point. I'm gonna ask you what's the probability that that data point lives in class Cj, okay? Likewise, we're gonna let P of X given Cj denote the conditional probability that a randomly sampled point from Cj is equal to X. In other words, if I tell you that I've sampled a data point from class Cj, what's the probability that the data point I sampled was equal to X? And let's let P of Cj denote the probability that a randomly sampled point lives in class CJ. Okay. So again, our goal is to come up with a classification rule where we can take a data point whose class we don't know or whose label we don't know and come up with a rule for predicting that class or predicting that label. Okay. So essentially, if we can come up with a way to model these probabilities, so if we can model, say, the probability of, if we can model the conditional probability here, if we can do this accurately, then this gives us a classification rule because if I give you an unlabeled x, we can just compute the argmax of this probability, this conditional probability. Okay. In other words, what we're going to do, if we get a data point whose label we don't know, however, if we know how to compute these things, then what we're going to do is we're going to compute all of these probabilities, and whichever probability is the highest, we're going to say that that's most likely the class that it came from. Okay. And so essentially what we want to do is we want to model these probabilities here. Okay. Now we want to do so we're going to proceed with that. Now in order to model these probabilities, you can probably sense that we're going to use Bayes' theorem somewhere. We're also going to need to make a few simplifying assumptions. So let's write those down here. So to model, let's do some simplifying assumptions. Okay. So our simplifying assumptions is we're going to assume that all data points live in one of two classes. C1 and C2. Okay, so we're going to, first of all, assume that we just have two classes to deal with. The second thing we're going to assume is we're going to assume that the classes C1 and C2 are independently distributed. And that each of them is an n-dimensional Gaussian with means mu1, mu2 respectively, and with a shared covariance matrix sigma. Okay, so what does this mean? Well, we've got our space where our data lives. We've got some mean mu1, and we've got some mean mu2. And if you sort of sample, if you were to sort of look at all the points in class C1, those points would all sort of live around U. Okay, so you can kind of think of there as being some like multivariate Gaussian distribution centered at mu1. And likewise, if you look at all the points inside C2, let me label this C1. If you look at all the points inside C2, you can sort of think of them as having been drawn from some sort of other Gaussian that sort of lives over here. So you think of there sort of being two Gaussians. One of them is giving rise to the class in C. The other is giving rise to the classes in, C1, and the other is giving rise to the classes in C2. And finally, like we normally do when we want to sort of model a probability, oftentimes what we have to do is we have to replace the actual probability value, which is 0 for any given, data point, or rather I should say like this probability here is going to be 0 for any given data point x, assuming it comes from a Gaussian. So we replace this probability here with the density function. Okay, so we're going to replace the probability that we actually want to model with the density function, with the Gaussian density function. So remember, we denote that by rho of x given Cj, where this is a normal distribution, where x is normally distributed with mean mu I or mu j. Gosh, things get sloppy here at the end. Mu j and covariance matrix sigma. Okay, so instead of trying to model these probabilities directly, which, these probabilities are actually 0, instead we're going to model them using our density function. Okay, and with that, I don't know how long I've been going, but I figure I've probably been going for almost 40 minutes, maybe 45 minutes. So I'm maybe going to stop there. The next part, we're going to kind of get really into like the maximum likelihood estimate part, and those computations can be kind of boring when you do them just, in a video. So I'd much rather do those in person for you in class on Monday, right? Yeah, I don't want to get bogged down on a video just doing a long computation. It kind of helps to have a little bit of razzmatazz there. So we'll pick this up on Monday. Have a great weekend. And if you have any questions, please write them down, because I'll take some time in class on Monday to answer questions you have from today's lecture.